So we've spent some time looking at the inner workings of an atom. In other words, what makes an atom tick? Why is it that magnesium has a certain atomic number while sodium has a different atomic number? What we're now going to do is we're going to take that information, what we've already learned, we're going to couple that with our nomenclature and how we can go about combining different elements to make new compounds. And we're going to now look at the next question, which is, how do my elements and compounds react with one another? Because we know chemical reactions are happening. We know that the whole point of chemistry is I wanted to create this thing, and I started off with these two things. How did we get here? Right? So these are important fundamental questions that scientists have been asking for hundreds of years. And if you recall, Dalton kind of set us on the path when he said that in a chemical process, the number of atoms must be conserved. So if matter is neither created nor destroyed, and we have the same number of atoms that we started off with at the end, what happens is that scientists started from that day forward really looking and measuring at how compounds and elements interact with one another. And in doing so, we started to see the relationships that occurred not only in certain chemical reactions, but how matter was conserved throughout an entire process. And so where we're going to begin our story now is this idea of, in a chemical process, matter is neither created nor destroyed, and as a result, we have to make sure that our reaction is balanced. Now, what do I mean by balance? Well, let's start off with a very simple reaction that you've probably seen or at least heard of a bunch of times. Whenever a rocket, whether it's the old space shuttle, whether it's the current SpaceX or any other rocket that's going up, but whenever a rocket goes up, usually that big, huge explosion that is producing a huge amount of thrust is a relatively simple reaction. It is a reaction between hydrogen gas, so notice that I'm going to write it as H2 because I remember that hydrogen was one of those diatomic molecules. So hydrogen gas reacts with oxygen gas to produce water. And so a couple of things that you want to notice right off the bat, because this is not a math equation, but a lot of times students kind of will equate the two, and that's not necessarily true. So first and foremost, we have on the left the things that did the reacting, better known as our reactants. I know we're very, very technical in our terminology. So these are our reactants. And then you have the stuff that was produced, better known as the products. I know, once again, we just blow ourselves away with our creativity. But here's the big kicker. The arrow does not represent an equal sign. This basically represents yields, right? It yields, it produces, it made. But what we want to be very clear about is that I don't want to assign it a quality, because equal often means that it can go kind of backwards and forwards. And we're not there yet. We'll talk about that, but not yet. For now, we're saying that this reaction proceeds from the left side over here where my reactants are to the right side over where my products are. So you want to make sure you're very clear on that. The next thing you want to look at is you'll notice that after each of my reactants and products, I seem to have put something in parentheses. I have a G on the left-hand side, I have an L on the right-hand side. And again, this should be fairly straightforward, but this represents my state of matter. So right now, this was hydrogen as a gas. This was oxygen as a gas. And over here, this is going to be water as a liquid. So that you're clear, there are two we didn't talk about. Of course, the one that you should immediately think of is solids. But there's another state of matter. And when I say state of matter, that's not the best word. Let's call it a phase of matter. And that is whenever you have a solution, right? So that's a mixture. That means that it's something usually mixed in water. For our purposes, it's almost always going to be water. But when you have a solution, we will often refer to it as AQ, where AQ represents aqueous. It's an aqueous solution. The word aqueous means of water, so in water. So again, typically in inorganic chemistry, our aqueous solutions, the solvent is water. Not always, but usually you can get away with it a lot. And so now that we have our chemical equation, what you want to do is you want to look at this because immediately something doesn't seem right. And what I mean by that is that when I look at my left-hand side, I count 2 hydrogens and 2 oxygens, right? So that seems to me, doing some quick math, is that I have 4 things sitting over there on the left-hand side. But when I go over to the product side, what I notice on the product side is that I only have 2 hydrogens and 1 oxygen. Well, that's only 3 things. So part of the problem right now is that if I left this reaction exactly how it was, where again, I did an observation, I had hydrogen gas, it reacted with oxygen gas, and I saw as a result that water was produced. If I left it like this, I have destroyed matter, and nope, can't happen, all right? Big no-no on that. So if I've destroyed matter, then the question is, well, how can I fix it? And what we're going to do is that once you have identified who the reactants are and who the products are, you do not alter their formulas. Again, you do not alter their formulas again. What we now do to balance this chemical reaction is we're going to add either more of the reactants that we have or more of the products. In other words, we're going to be placing new coefficients in front of each species. We are not going to alter the formula, because it would be very easy for me to sit there if I wanted to make a big whoopsie doodle to go, oh, you know what? I meant to say that over here I had hydrogen reacting with oxygen. But here's the snag. That's not what oxygen looks like. We know that oxygen is going to be a diatomic molecule, and it's almost always going to come up as O2. So to fix this, what we're going to do is we're going to use a method known as inspection, where basically what we're going to do is we're going to make sure, we're going to do advanced bean counting now, and we're going to make sure that however much I have on the left, I have the same exact amount on the right. Right, so I'm going to make sure that I'm working both sides evenly. So the way I do this is pretty simple. I start off and I ask, how many hydrogens on the left? Seems like I have 2. How many hydrogens on the right? 2. Yay! Balanced. But then, how many oxygens on the left? 2. How many on the right? 1. Ruh-roh. So to fix it, I'm going to stick a 2 in front of the water. But the moment I do that, ruh-roh, who did I mess up? I messed up the hydrogen, which means in order to fix it, I have to come back over here and I have to put a 2 in front of that hydrogen. Now, once I do this, what we'll notice is that we're going to have 4 hydrogens, I do correctly, 4 hydrogens on the left, and I now have 4 hydrogens on the right. I have 2 oxygens on the left, and now if I look closely, this water here had 1, but 1 times 2 is 2. So this is now a balanced chemical equation. And in balancing it, notice what I did. I've created a ratio between my reactants and products. In other words, now in order for this to occur, here's what we're saying. We need 2 hydrogens to react with 1 oxygen. And when that happens, I produce 2 waters. Right? So this is how balancing chemical equations is going to work. So we take it one step at a time, one tick at a talk, and you'll be there in virtually no time.